over the smooth area and securely fasten it down with the pins included in the compaction kit. The next step is to dig a hole to a depth of approximately 4 to 5 inches deep and to the same diameter as the hole in the base plate. This depth should provide a proper volume based on the maximum particle size. Caution should be taken when removing the soil from the test.
So notice how he's very careful about not losing any soil. So this is probably easy to do for, silty sand, but it's less easy to do if you have a lot of clay stuck to the blade, or you have very coarse ground material and it just drops everywhere.
So that none of the material is lost. A fine brush is used to remove soil particles that may be clinging to the auger. The material retrieved from the hole into a non-absorbent, moisture-tight container. Make sure the container has a lid that can be securely tightened. Once all the material has been removed, seal the container to prevent loss of moisture. Soil at the bottom of the walls of the hole as smooth as possible.
And then he'll try to smooth out the hole.
Is ready. With the valve closed, invert the cone with the sand-filled jar in the center hole of the base plate. Open the valve so that sand flows down into the test hole. This part of the test should be done in such a way that the sand cone is free from any vibrations or disturbances during the flowing of the sand. Vibrations can affect the bulk density of the sand and decrease the accuracy of the test. Once the sand flow stops, close the valve and remove the sand cone apparatus.
So notice how he can be a bit more sloppy afterwards, because he doesn't really care about the weight of the entire device before and after. Here, the technician's measuring the weight of the soil removed from the ground, so I guess the technician teared this container beforehand.
With the soil removed from the test hole, sand cone apparatus, and record. The difference between the initial weight of the sand cone apparatus and the final weight are used in the calculations to determine the weight of the sand needed to fill the hole.
So that's in essence how a sand cone replacement test looks like. And in class we went over how to do the calculations together. And inside that red container where the soil was extracted, you would bring it back to the lab to obtain the moisture content. So that's the sand cone test. Other things that I promised to show you include the rubber balloon test. So we can look at this together and fast forward where we need to.
Procedure for conducting a soil density test using the rubber balloon method. The selected base pickings are taken at each test site.
So the entire procedure is quite similar to the sand cone test, where you dig a hole in the ground.
A dozer or other construction equipment may be used to place the booted in the compaction kit. The base plate must place the volume measure on the base plate for the initial reading. Once the device is in place, using the bulb type pump and while holding down the volume measure, force the water down into the balloon until resistance is felt. Apply the calibrated pressure and note the reading on the glass cylinder. After the reading is noted, reverse the bulb type pump in the quick coupler and pump the water back up into the graduated glass cylinder.
So the reason we obtained the initial measurement is there's still some space between the rubber membrane, and even though there's no hole in the ground right now, we still want to know what the zero measurement is.
For the reading, The next step in the rubber balloon test procedure is to dig a hole with a soil auger, trowel, or other tools. The hole must be 4 inches in diameter and approximately 5 to 6 inches deep to get required amount of soil needed for the test. Exercise care in digging the test hole so that soil around the top edge of the hole is not disturbed. As demonstrated here, through the compacted soil is reached. Place all of the loose material from the hole.
So the procedure is more or less like the sand cone test. You have to be very careful not to lose any soil. You can imagine this is quite difficult to do on site if you don't have a lot of space, like this technician does.
In for weight and moisture. All material from the test hole must remain within the vertical sides of the base plate, which is our point. Use of a brush to move the material and quickly to the sample container before proceeding with the rest of the test. Place the volume measure back on the base plate in the same initial position. While holding down the device, pump the balloon down into the hole and apply the calibrated pressure. Lightly tap the gauge to help stabilize the reading. Once the final reading is noted, reverse the bulb-type pump in the quick coupler and pump the water back up into the graduated glass cylinder. Generally, earth moving.
So that's the procedure for rubber balloon, and it's very simple. It's simple in that the principles are the same for sand cone replacement test. Now, the last quality control field compaction test I'd like to show you is the nuclear densometer that we were talking about.
Before each day's use, refer to CTTP test location. Prepare the test site by leveling and smoothing the surface using the scraper plate. Remove any loose material. Do not fill more than 10% of the footprint of the gauge. The plate should sit left. Step on the middle of the scraper plate and place the extraction tool over one of the risers. Insert the drill rod in the same riser and hammer it into the ground at least 2 inches deeper than the desired test depth to protect the source rod. The test depth should equal the lift thickness when possible, but should never exceed the lift thickness. Most drill rods have markings which can be used to determine the depth of the hole and include the extra 2 inches for source rod protection. While standing on the plate, pull up the extraction tool using a twisting motion to remove the drill rod.
So this looks very calm and civilized, but sometimes if you run into core stones, you won't be able to get the peg back down. Then you have to find another location and repeat.
In the scraper plate, mark the hole feet from the test area.
So after you remove the plate, then you can move the nuclear densometer
from the test area.
And you form the hole where you can place the probe in.
Align the gauge with the footprint. Place the source rod or front rod over the test hole and align it with the guide marks. Input the gauge parameters for time, depth, and the Proctor value. Use the up or down arrow keys to set the times to the test using the up and green use button. Lower the source rod to the test depth by pulling back on the trigger and pressing down on the indicator at depth. The source rod will be in full contact with. Move away from the gauge at least 3 feet. After completion of the test, save the rod by pulling up until the rod is all the way up. Record the data.
That's essentially the data you get. Wet density, dry density, moisture content, and if you plug in the maximum dry density, then the probe will give you the degree of compaction as well. Some devices have GPS recording, so you know which location you took it. So in essence, these are the 3 main approaches we use for quality control in the field. So that's where we ended off last lecture, and if you recall, we finished shallow compaction, and in today's lecture we'll transition to deep compaction, and I think we have some time to move on to our next module, which is on consolidation, surcharging, PVD drains, and so forth. So you can probably guess that the term shallow compaction refers to probably less than a meter. And if you remember some of the graphs I showed you, even if you do several runs over a particular site that you're trying to compact, the maximum depth of compaction might just be 0.5 meters, right? In this case, for deep compaction, we're talking about depths greater than 6 meters. So what does this mean? Well, you can do the compaction job a bit faster because each lift can be thicker. This can minimize cost overall for a particular project. And you can see at the top of the slide, we've outlined the definition of what we mean by deep, intermediate, and shallow compaction. For some of the approaches we talk about, you can even reach depths greater than 6 meters if needed. So let's take a look at what deep dynamic compaction is. There are, in essence, two approaches. If you remember from the last slide, we have dynamic compaction and vibro compaction. So these approaches are more empirical, based on experience, and depends on the quality of the contractor on site. So there's less calculations we can do for this particular part. But it's nice to know that these options are available for you if you're a geotechnical engineer for a particular project. Now, deep dynamic compaction relies on very high impact energy so that you can get to the depths that you cannot for shallow. So one of the ways to do this or to achieve these high energies is by dropping a very heavy weight after suspending it quite high in the air. And you can see in the bottom right photograph here, Boschy Solantage is carrying out deep dynamic compaction in Hong Kong, actually, for a Hong Kong project. And what you see is debris splattering everywhere after the weight has been dropped from the crane. There are certain types of soil that are more suitable for deep dynamic compaction. And since this is an experience-based type of compaction effort, often you see that it's related to plasticity index, Atterberg limits, but generally if you have loose, saturated fill, silts, and clay soil with low degree of saturation, these soil types are ideal for deep dynamic compaction. It's not so much recommended for clayey soils. The reason being I'll explain later, but you can probably guess for clayey soils, permeability is very low. It's going to take a lot of time to generate and dissipate pore pressures. The timescales are entirely different, right? And to some extent, the point of dropping a very heavy weight in the ground is to perhaps dissipate some of these pore pressures. Anyhow, some of the applications for deep dynamic compaction are listed at the bottom. If you want to increase the bearing capacity of the soil, you want to reduce compression by increasing settlement through consolidation, it works as well. For places that are susceptible to liquefaction, seismically active regions, you can reduce the liquefaction potential of the soil. That's what deep dynamic compaction is commonly used for open sites. If we take a look at the top right of the slide here, you can see that there's essentially a particle size distribution curve, and we can see that in this region here, we're less willing to do deep dynamic compaction, whereas zones 1 to 2 are still reasonably suitable for deep dynamic compaction. So that gives you an indication. Now, in a very simple summary, table, here are the advantages and disadvantages of deep dynamic compaction. Advantages we mentioned, because you can reach deeper depths with the higher impact energy, you have shorter construction time, lower cost. You can also see points where there are collapsible soil stratum on site. That's why we say you can use to detect weak areas. The equipment required to do the job is quite simple. You just need a crane and a weight. The disadvantages, well, there seem to be quite a few. You are probably less likely to use this for clay soils because permeability is low, and when you generate a very large impact energy by dropping a weight, there are lots of excess pressures that need to be dissipated. If you can't dissipate these pressures, then you just have something that's very liquefied and watery on site. You're less likely to use this inside urban areas because of the pollution from noise and vibration. You probably have to have a very rigorous instrumentation program to detect the PPV, peak particle velocity, around your site. By inducing a vertical drop impact, you're also causing a crater. And a crater also means you have horizontal stresses in the ground. And you have to decide whether you're able to tolerate this kind of lateral movement in the ground. And you can imagine such high impact energies will lead to vibrations that might cause damage to neighboring infrastructure. What we mean by damage is cracks. It may happen, right? And we talked about vibration monitoring, and you probably need more care in terms of safety because you're dropping quite a heavy weight from up high. And there are sites where you don't have a lot of headspace, so this is really only reasonably used for sites where you don't have clearance constraints. And if you mobilize a lot of cranes, it could be costly. For a large site, you probably won't just use one crane, you'll use several cranes, right? Because the impact area is still restricted. Now, let's look at some of the mechanisms behind dynamic deep compaction. Of course, the major mechanism that we want to see is just densification of grains. Just like shallow compaction, we want to remove the air phase and we want to rearrange the granular assembly so that it's in a denser configuration. And by dropping a very heavy tamper, we can actually generate a denser configuration of the grains and reduce the voids by expelling air. This is the same as shallow compaction. Another way is by dropping a very heavy tamper on the ground, you also form some sort of plug directly underneath. And you can imagine that on a site, you would do this systematically in a pattern to have the entire coverage for the site. So the first mechanism is densification, which is no different than shallow compaction. Now, the second mechanism that's a little different that we don't try to achieve in shallow compaction is dynamic consolidation, because we often try to differentiate consolidation from compaction. But whether we like it or not, when we drop such high impact energies on the ground, we will generate excess pore pressures in the soil. And it depends on whether you can dissipate these pore pressures. We mentioned that if you have low permeability like clays, you'll be unable to quickly dissipate. It'll take a long time. And often when you're doing dynamic decompaction, you want to successively drop the weight in very short time intervals. So you don't want to wait for pore pressures to dissipate. If you keep on causing undrained loading by successive drops on very low permeability soil, then the soil can liquefy. And you're essentially trying to tamp water, right? So it's not going to densify any further. There are four main mechanisms related to dynamic consolidation that you can see here. We have the natural compressibility of saturated soil. You can have liquefaction where you lose all the effective stress. You can change the permeability, and last but not least, there's thixotropic recovery. So we can look at each of these mechanisms in a bit of detail. So in terms of compressibility of saturated soils, under undrained loading, we can see that saturated fine-grained soils is largely incompressible. You're not going to get any volume change, right? So there is probably a very small element of elastic compression, but we're talking about a very small percentage that's probably negligible compared to subsequent consolidation. So although this is listed as one of the mechanisms, it's definitely not the primary one. Menard and his colleague in 1975 attributed volume change to dissipation of air bubbles, saying that the soil is not completely saturated, and this can attribute to up to 4% volume change, which is actually quite insignificant. So although this is listed as a mechanism, let's take a look at the more dominant mechanisms that drive this dynamic deep compaction. A more dominant mechanism is likely the generation and dissipation of excess pore water pressures. And as we mentioned, dissipating these pore pressures will relieve the soil, and you'll see compression just like consolidation and settlement. And when you have compression and settlement, you have a denser grain arrangement, you have stiffer and stronger soil. So more or less we're talking about consolidation, but applying dynamic loading to the surface and rapidly dissipating these pressures. And moreover, we see that low permeability fine-grained soils are not suitable for the task at hand. And when we talk about PVDs later, prefabricated vertical drains, and you can also use these drains in conjunction with dynamic deep compaction to increase the composite permeability of the ground and to accelerate the dissipation of any excess pore pressures generated from dynamic deep compaction. Two other mechanisms involved change of permeability. When you apply very high impact energy to the soil, we're not talking about mesoscopic permeability, we're talking about generation of fissures. You can cause very large fissures in the ground where these fissures act as a preferential path of dissipation for pore pressures. So depending on your soil type, it has to be cohesive, right? If you want fissures and tension cracks, you need cohesion. And you've learned that from your basic soil mechanics class. So if you have sufficient cohesion in your soil and you have high impact energy and you generate localized fissures, these fissures act as preferential flow paths for the dissipation of pore pressures. Very much similar to if you have trees and the roots are coming on the ground, perhaps these tree trunks and roots provide preferential flow paths for rainwater to infiltrate in the soil. It's a similar concept. So, and that's what we mean by change of permeability. And the last mechanism is thixotropic recovery. Now, if we want to understand what thixotropic recovery is, we can take a look at the schematic or the graphs on the right of the slide here. You can see that each of these plateaus, increase in plateaus, let's take a look at this first one, is an application of energy. And we're essentially showing the accrued application of energy here. So with each drop, you accumulate further increase of applied energy to the ground. And likewise, you would expect through all four mechanisms that we talked about, except for thixotropic recovery, we haven't covered that yet, you have accumulated volume change in the ground. And this volume change will sharply increase each time you drop the weight on. And the plateau means there's no further change in applied energy. It's only accumulated energy up to a certain time interval. If you look at the third graph below, you can see that each time you apply a dynamic tamp to the ground, you ramp up the pore pressure significantly. Degree of liquefaction 100% means you've lost all effective stress in the soil. It's liquefied. And after it liquefies, it has to dissipate pore pressure of the soil, and then hopefully you can reach a denser configuration each time. Now, in terms of bearing capacity, this is where we want to talk about thixotropic recovery. Sometimes if you have clay suspensions, by dropping a dynamic load on a soil and you liquefy it, it becomes like a fluid, like a clay suspension. So interestingly enough, we can see that by applying dynamic loading through intervals, although we lose all the bearing capacity, you can see here each time through effective stress, and if you keep on repeating the process, there is some progressive gains in strength each time with repeated impact. And this is a unique principle of suspensions, clay suspensions. So it's coupled with the task of liquefying the soil. So that's what we mean by thixotropic recovery. Now, this is of course only for very specific clay type soil. If you can liquefy it. For granular materials, you probably don't want to hear too much about thixotropic recovery because it's not one of the driving mechanisms. Okay, so that's the basic ideas behind deep dynamic compaction. And you might be wondering, well, how do we do this on site? Well, you would mobilize numerous cranes, and each operator will systematically drop these weights onto a site following a set pattern. And you would do this in phases, right? So for phase one, you can see at the top, it's anything with a circle. You would do this kind of pass first. And then for phase two, you would go in between anything you first missed with the first pass or the first phase. And then with phase 1, 2. Phase 2 is when you cover everything again through a lot of passes. So it'd be a systematic pattern of dropping weights, essentially. And you can see this is the plan view. If you look underneath what happens with each phase. During phase 1-1, you're looking to reach different degrees of improvement by carrying different passes. So phase 1 is more or less this line here in the red. And you can see how that differs in property. Property can be anything. It can be strength, stiffness, depending on what you're looking to improve. And each time you do a second pass, you can see a slight improvement with increase in stiffness or strength of soil. And after phase 1-1, 1-2, and 2, you can go through the entire site again through what they call an ironing phase. And this is the typical empirical cross-sectional improvement you're expecting to obtain. And this is, again, highly empirical based on the experience of an operator. And if you're wondering what kind of improvements you can get in depth, well, here it's indicative, right? Where the peak improvement occurs, but it's just for frame of reference for you. Nothing to remember here, except that this is actually highly empirical, depending on what type of temper you use, what type of weight, what type of underlying geology, what type of soil you have, and degree of saturation of the soil involved. But this gives an overview of the construction process. With deep dynamic compaction, there are, of course, other considerations. If you have very soft soil at the top, then this is probably not going to work because you won't be able to get your cranes in there. The cranes cannot even walk on this type of, or travel on this type of soil. So you would probably have to stabilize this first by removing it or adding in another engineered fill layer on top. In contrast, you can have the other extreme where you have a very hard layer on top. And if it's a very hard layer, you're not going to get the four mechanisms that we talked about earlier. Because you're unable to transmit energy with depth, you'll probably end up transmitting energy laterally or radially because of this hard layer. So these are the two conditions where deep dynamic compaction may not be so suitable due to the constraints of a site. Now, if your site has a very high water table, this is also a problem. You can imagine that you'll be liquefying things very easily and you're just trying to dynamically tamp water. That's not going to get you any substantial improvements. So these are some considerations that just need to be considered, and it's difficult to do calculations for deep dynamic compaction because the calculations are largely empirical. And they're so empirical, in fact, that the equations used are not even dimensionally correct because it's based on experience and curve fitting. But I think this is all we need to know in this class for deep dynamic compaction. It's not very common that we encounter it in geotechnical projects. Perhaps we use it for very large-scale reclamation projects. Other than that, it's not routine thing we see in Hong Kong. So that's dropping a weight onto the ground, deep dynamic compaction. Now, another approach also falls under the realm of deep dynamic compaction. We call it vibro compaction. This is a bit different. We actually have to insert a probe into the ground using this approach. We have used these vibro compaction methods in Hong Kong as well for our land reclamation projects. The premise of vibro compaction is you have some probe that has a vibrating device inside, and you put it on the soil, and under its own self-weight, you turn the vibrating motor on, and it just destroys granular contacts. Just like for granular materials in the lab, if we want to densify, we put on a vibration cable. And what vibration does is it disrupts grain contacts. So you see my knuckles are grains. It will cause slips in these frictional contacts, and you'll get a denser configuration. Now, this is the same principle here for vibro compaction. You're mostly targeting granular material here by disrupting these frictional contacts among grains and densifying the granular arrangement. Now, in saturated geomaterial, vibration will also generate excess pore pressures. And excess pore pressure serves to push grain contacts apart, right? So that's another mechanism at play here. In dry gravel or dry coarse sand, to ease the process of disrupting these frictional contacts, we understand the principle of effective stress, and reducing effective stress can be done by increasing pore pressures. Now, pore pressure doesn't have to be water, it can be air as well. You can have air injection, water injection to disrupt granular contacts, to densify the soil, and that's what vibro compaction generally refers to. And you can imagine that the vibrating probe will have attenuation in energy in the ground radially from the probe. Now, we mentioned there's two types of vibro compaction. There's vibro compaction with and without backfill. At the bottom of the picture here, you can see that here is the probe suspended by a crane. It's being placed in the ground under its own self-weight and vibrations. As you do this, if you want to do vibro compaction without backfill, then you ignore this material here. But if you're vibro compacting a region, you loosen everything, and you can place gravel or coarse sand in to further densify this region locally. And you can imagine, just like dropping a dynamic tamper, you would do this systematically on a site, and you would have a composite improvement in the ground. So this is what we mean by with and without backfill. Now, we mentioned that there are other fluids you can place. So vibro flotation, vibro flot are commonly used words as well. Some of these refer to the use of air instead of water to increase the degree of dry density in the ground. Generally, there is a suitable range for vibro compaction. You can see here that the most advantageous type of soil is, we're talking about granular materials. That's what we mean by cohesiveness. It's not so useful for clayey soils, right? And you don't want too many fines. If you have too much silt or clay, it's not, again, very suitable, because this is a mechanism designed to disrupt frictional grain contacts. So we want coarse granular material in this case. You might be thinking, how do we characterize the ground improvement for such complex empirical methods? Well, what do I mean by that? How do you know as an engineer that the strength and stiffness properties of a site have improved? We'll spend some time on a module later related to in situ measurement of soil strength and stiffness. Some methods we can use include SPT, CPT. CPT probably less reasonable for granular material. to get the in situ profiles of the strength and stiffness before and after improvement. So if you look at this graph, you can see SPT. What is SPT? Well, it's something encountered all the time in geotechnical engineering. It's a very quick way to get in situ strengths. I'll spend an entire module on SPT testing, so don't worry about that. Just appreciate that it's a way to test how much your site has improved. We can see that before improvement, you'll have some curve like this. After improvement, you have some curve like this. And an increase in SPT value generally means an increase of strength or stiffness of the soil. And look at how these curves are decreasing towards the right of this graph, meaning that if we increase the fines content, whether it's silt or clay, then vibrocompaction becomes less suitable. So if you're asked what type of soil vibrocompaction is suitable for, you can probably guess it's suitable for granular type material. Similarly, if we look at another PSD type representation, we know that zone A is the most suitable for vibrocompaction, particularly gravels, coarse and medium grade sand. You can also work in zone B, but once you reach zones C and D, where you find sand, silt and clay, you're probably not going to want to use vibrocompaction. And at the bottom of the slide, there's some other notes. This has been well stressed over the past 30 seconds. If you have dry gravel material on site, you can also use injection wells to put water into the ground to increase pore pressure so that your vibrocompaction effort becomes more effective. When you vibrate, create excess pore pressures and further disrupt effective stress or the frictional granular context. And vibrocompaction can reach substantial depths of 40 meters. And you might be wondering, when is this useful? Well, let's say you don't have the time to go lift by lift, 0.5 meters by 0.5 meters. And let's say you're doing a reclamation project and you just dump a sand blanket on top. And this sand blanket, we're talking about 10 to 20 meters in thickness. Well, then you can still compact it. What you do is you come back afterwards and you carry out deep dynamic compaction, whereas shallow compaction is for projects where you can afford to go lift by lift and compact and check. For most reclamation projects, we tend to adopt deep dynamic compaction after putting, let's say, sand blanket on top or a fill surcharge on top to densify it further. So that's when vibrocompaction would be used. And likewise, with dropping a dynamic tamper, we want to increase bearing capacity, reduce settlement. For seismically active regions, again, reduce liquefaction potential. Advantages of vibrocompaction. It's not as quick as dropping a weight because you have to insert the probe in, and if you're doing backfill, it takes more time, but it's still quicker than going lift by lift for shallow compaction. It's well proven to work in the industry, locally and globally. And it's also useful for granular material that's submerged because the water phase actually helps to increase pore pressures and disrupt grain contacts. The disadvantages and limitations with vibrocompaction, perhaps it's not suitable for soils with high fines content, with high silt and clay content. And just like dropping a dynamic tamper, you will induce vibration, and it depends on whether you can tolerate that with your neighboring infrastructure. The vibrations can cause near-field effects in settlement and can damage nearby infrastructure. That's why we don't really use it inside urbanized areas. If we want to take a look at some of the fundamental mechanisms, just for interest, of vibrocompaction, it's nothing too complex. If you look at the top of the slide here, there are empirical conceptual diagrams of what happens radially from a vibrating probe. So if this is your vibrating probe, there are 4 regions. they have a dilatory region, fluid dye zone, a compaction zone, and elastic zone. And you can see that there is a sweet spot in terms of distance from the probe. Somewhere between the second and third zones, you can get the maximum soil density and you get attenuation of density with radial distance. To where you reach the initial density, you're not getting any further improvement. That's what elastic zone would imply, right? Anything you try to change just goes back to its original form. In terms of particle acceleration, you can see that there's attenuation with the particle acceleration, or PBV, with distance from the vibrating probe. So this is just conceptually showing you why you would need to do a systematic pattern for vibrocompaction as well, because you do lose vibratory energy with distance from the probe. And most contractors would understand where they have no further benefit from vibrocompaction, and this will dictate how close you have to do each probe. And of course, there's other supported empirical data. Here it's from Arnold and Hurley. You have void ratio on the y-axis, and you have radial distance from the vibrating probe. And you can see in both cases, there is a distance where you have the law of diminished returns. And likewise, after a certain number of cycles, in this case, 60 cycles, you're not really getting substantial improvement. If you increase by 80, 100, and 120. By cycles, we're talking about how many times you cycle the vibration process by lifting and extracting and putting the probe back down in the ground. You can also probably guess that when we place the probe in and when we pull the probe out, we have to apply different frequencies, right? So you can see from this graph that on the y-axis we have depth, x-axis we have time. And normally during extraction and insertion of the vibrating probe in the ground, they carry out this at a high frequency, so you disrupt the contact, so it's much easier to get the probe in the ground. And you can imagine after you densify it for a while, your probe might be very difficult to raise with the crane. So we increase the vibrating frequency to get the probe off the ground, but what we do normally is we let the probe sit after we've inserted it to the target depth, and then we reduce the frequency. And this is called the compaction phase. And these frequencies probably have little meaning to us, but if you're interested in what type of frequencies we're looking at, during penetration extraction, it's about 30 hertz or greater. During the compaction phase, we reduce that by a third to maybe 20 hertz or less. And similarly, with the effects of distance from the vibrating point, we can see that on this graph we have the degree of influence. So this is the influence zone. This is distance from the compaction point. And we have 3 graphs with increasing compaction energy. The more fines you have, and we know that this is less effective, and the degree of influence will also decrease from the compaction point. And this was established earlier on. There are, of course, other fine considerations to require. We can carry out different performance criteria for different applications. If you want to use vibrocompaction to form a foundation to support floor slabs, tanks, embankments, this is the target relative density you're looking at. If you're looking at bridge foundations, this is the target relative density. And for very high threshold or high tolerance machinery foundations, this is the target relative density. And you can also overlap these vibrating points to form composite foundations to place perhaps slabs or rafts on top if you overlap them. You can use it to form a wall as well, a very thick composite foundation column as well. So there are different ways to use fibro compaction. So that's all I want to talk about in terms of deep dynamic compaction. As you can see, most of the stuff is very empirical, depends on the contractor, whether you have an experienced contractor. Most of the core content I want you to understand is related to shallow compaction. That's why we did some sample calculations together. Now, let's move on to the next topic. Or should we take a 10-minute break? Let's take a 10-minute break, and then we'll carry on with consolidation. All right, let's carry on. So for a new module, the topic's on consolidation. This is a very important topic to cover because a lot of land reclamation projects require geotechnical engineers to have a very strong understanding of consolidation. And you'll find that when you carry out your job interviews in the coming months, let's say January, February, whether it's a graduate geotechnical engineering office position or whether it's AECOM or ERIC, they tend to like to ask technical questions related to consolidation. It can be something very simple. How do you calculate the degree of consolidation? And it shouldn't be a complex answer, right? If you know the change in pore pressure relative to the emissions, surcharge, excess pore pressure, it's just a percentage, right? So I think it's important to spend a bit of time on consolidation, just as a geotechnical engineer and for ground improvement, in order for us to understand how to exercise the installation of PVD drains, applying surcharge loads, how does that affect consolidation? So that's why I spend a bit more time on consolidation, because it's important, and this is probably for most of you your last chance to go over consolidation before going to industry. Otherwise you won't remember since your soil mechanics class. Anyhow, there are some expected outcomes I want to achieve in this particular module. We will spend time to recap existing fundamental principles of consolidation. Consolidation questions are very easy to ask for assignments and exams. So I think it's worthwhile to go through some existing fundamental principles. I want you to also understand what's going on in the lab when you, as the geotechnical engineer, proctor some odometer tests. What parameters are you getting? What are you asking for? How to interpret the laboratory test results? So we'll go over that as well. You should also be able to calculate very simple back of envelope estimations of what's the expected primary and secondary consolidation. Why do we need to know this? Well, for any land reclamation project in Hong Kong, one of the highest priorities is time. Your client will always ask you, when can we use the land, right? So we need to be able to predict when. That's what I mean by time rate of primary consolidation settlement, but you also need to calculate how much settlement will there be. How much settlement is very important, because if you have a lot of settlement of your clay, what does that mean? Well, you need more sand. You need more sand to replace the volume that you lost from compression. And we can probably hear from the news that sand is rather difficult to come by these days, right? And difficult, meaning that it's expensive to buy as well. So these are very important things we need to be able to calculate for land reclamation projects. After we review some of the fundamentals of consolidation, we can look at how to surcharge preload a site. We can also look at how to install PVD drains and look at how we can apply different ground improvement techniques to reduce settlement. Although settlement is something we're interested in reducing, do note that it costs time to cause compression, and it costs money as well. So these are important things we need to consider when we cover the topic of that come after consolidation. So, blast back to the past for soil mechanics. What is soil compression? Well, soil compression is essentially a reduction in volume. Anytime you apply surcharge load or a total stress to a particular soil, you should, in principle, cause some compression. And compression can occur in different ways. And even if you have a site that's fully been or finished primary consolidation settlement, you'll still get some degree of compression. Compression can be caused from deformation of soil particles, and this is of course elastic. So if you remove the surcharge or total stress, you'll see recovery in these strains. You can also get compression from intergranular rearrangement by getting lower void ratios as grains get tighter and closer to each other. You can also get compression, lastly, from the dissipation or expulsion of water and air. And air was something we looked at in compaction. Here, we try to devise geotechnical means to remove water from the soil by reducing the voids. Soil settlement can be characterized in terms of calculation, in terms of three aspects. The first is elastic settlement. So we mentioned that this is the elastic deformation of your soil without any changes in the moisture content of the soil. And you can probably expect that this component is not significant, right? Otherwise, we wouldn't have any trouble compressing soil and reclaiming land. The main problem we have is primary consolidation. That's where we have any volume change due to dissipation of excess pore pressures in the soil. Now, there's also something called secondary consolidation, and this has nothing to do with the dissipation of pore pressures. This has to do with the rearrangement of the soil fabric after you've already completed primary consolidation. And there are, of course, ways to estimate secondary consolidation. Secondary consolidation is often referred to as creep in the soil. And for any land reclamation project, we're not just interested in primary consolidation. We also want to be able to predict, let's say 10 years from now, will we still have a settling ground? If we do, what's the order of magnitude we can expect? So for any reclamation project, we have to understand how to calculate primary consolidation and secondary consolidation settlement. We're less interested in the elastic response of the soil from loading and unloading. Now, let's recap some basics, soil mechanics, drain and undrained conditions. You have to have a strong grasp of this if you want to understand the concept of consolidation. Now, if we look at the left side of the slide, in the yellow box, we can sort of use an analogy of a bag of crisp as drained. If we have the crisp open, the interstitial fluid is the air phase. So the air can leave and enter the bag of crisp as it wish, and the porosity is quite high. The permeability of this chip bag is quite high, right? And when you load this bag, you transfer the loading from this plastic bag to each individual chip. And you can imagine each crisper chip is a soil skeleton, right? So this would be a drained situation. As we load the soil, we do not generate any excess or fluid pressure. Fluid in this case is air. We do get volume change, however, right? As you load the crisp, let's assume the crisps are really strong, we can't crush them, okay? But they will still rearrange the crisp. So this rearrangement of crisp, a different pattern, they connect with each other, will cause volume change. So the important thing to remember is when we talk about drained, we're talking about no generation of excess pore pressure. This is of course idealized, and we get volume change for drained conditions. In contrast, for undrained conditions, we can imagine, well, not the same bag, it looks different, a similar bag of crisp, but it's closed, or it's not open yet, this chip bag. So no matter how you load it, you're actually not causing volume change. You may deform the chip bag, right? If you load it this way, it'll try to expand the other way. And as long as you don't tear the chip bag, you're not getting any volume change overall. It remains the same. But what does happen with a closed chip bag? When you load the chip bag, what happens is, well, you're loading the pore fluid, which is the air. The air is meant to protect the crisp, right? When we're transporting it from the supermarket, from the factory to your home, so you don't have a bunch of crumbs. You're not eating a bunch of crumbs. You're eating crisp, right? So undrained loading, what happens? We have to recall that there's no volume change for undrained loading. Okay. Yeah, there's deformation of the chip bag, but overall you're not getting any volume change because you're not getting any dissipation of the pore fluid, which is air. You're also generating excess, well, in this case, it's not water pressure, excess air pressure in this case, but you can imagine if this was analogous to soil, you're generating excess fluid pressure because you're mainly loading the air in the chip bag, right? So if you try to conceptualize a chip bag as drain and undrain conditions, it might help you to understand consolidation a bit better. So I just wanted to throw this in here, since it's a recap. Now, another important fun fact, I guess, about drained and undrained. We often have this mentality that, I'm not sure where this is from, I'm guessing it's from your undergraduate textbooks. When you hear the word undrained, what type of soil do you think of? You tend to think of clay, right? And when we think of drained, you tend to think of sand, right? So automatically, in our minds, as young geotechnical engineers, we assume that clay must be undrained, sand must be drained. Well, this is conceptually, there's a shortcoming with this, right? It's not always true. Whether something's drained or undrained depends on two things. The first is the rate of loading and the rate of pore pressure dissipation. What does this mean? Well, even for sand, it can be undrained, right? If we apply very high dynamic loading to the sand, such as earthquake loading, there's actually no time for the pore pressure generated to dissipate because the rate of loading is much higher than the rate of dissipation. Now, what controls the rate of dissipation? Well, the flow of fluid leaving your soil. And we know that flow in soil is governed by Darcy's law, right? These are common interview questions. V equals minus Ki, Darcy's law. And what do we see in Darcy's law? Well, we see permeability, right? Depending on the permeability of your soil, this permeability will control the expulsion or the dissipation of pore pressures. So it's important not to get confused that sand must be drained and clay must be undrained. It's more complex than that. It depends on the rate of loading and the rate of dissipation. So sand can be undrained, right? And it depends on what problem you're talking about. If you're talking about clay, but you're giving it a time scale of 1,000,000 years, then it can be drained as well, right? So remember these things. And some of the things to just remember, another common question that we're often asked under pressure, what's the typical permeability of sand, silt, and clay in meters per second, right? It should be easy for you to remember, right? You have to know this stuff because permeability is not about exact numbers. It's about order of magnitude, right? We care about the general order of magnitude. So a quick rule of thumb is if you have sand, silt, clay, you know that. If you just remember these numbers here, of course everything is metered per second, then you'll always remember what the typical permeabilities of these soils are. So if you're working as a geotechnical design engineer, your boss asks you, what's the typical permeability of silt? And you have 10 to the minus 7. Then you know it's probably the right order of magnitude, right? If you have 10 to the minus 10, you know that's very much impervious, right? Clay is very impervious, right? So it's a good way to remember, right? 3, 6, 9% of clay. Just a quick way to remember permeabilities, okay? Permeability always talk about order of magnitude. We're not caring so much about precise number, because it's not that important. And if you're interested in what's happening with the derivation of permeability related to hydraulic gradient, and somehow this is derived for you here, you can take a look at this at your own leisure. On this corner of the graph, or the slide here, we see typical rates of loading. Not in any unit that is useful for us, but we can see that if we have earthquake or dynamic pile driving or dropping a tamper onto the ground, you generate loading in the scale of less than a second, right? And if you're talking about natural erosion of a geological stratum, we're talking about 30 years, more than that, right? And then there's other things in between. So when we want to characterize whether something is drained or undrained, we need to think about the rate of loading. And a lot of the times when we do calculations, we know we have to do total stress analysis and effective stress analysis. We can talk about that in a bit, but we usually carry out both. I mean, we don't really always understand what the rate of loading is. And to be conservative, we often check for both, right? So the main point I want to stress as a recap is when we try to distinguish between drained and undrained loading, we care about relative rates between loading and the rate at which the pore pressure can diffuse or dissipate from your soil. So there's no such thing as sand must be drained and clay must be undrained. So these diagrams are quite easy to understand for us if we've taken soil mechanics, right? If we want to further break this concept of drain versus undrained down, we can use these graphs now. For triaxial tests, when we're talking about drained and undrained, it's less complicated, right? We can just turn the valve on to allow pore pressures to dissipate from your triaxial specimen, or we can turn the valve off and not let any water leave, right? And if you understand this concept, it's quite easy to understand why for undrained triaxial tests we have what? We have no volume change, right? If your pore pressure cannot dissipate from a saturated soil, there's no air in the saturated soil in the triaxial test because you've purged all the air. If you don't let any fluid dissipate, then there's no volume change because there's nowhere for the fluid to go, right? And anyhow, let's take a look at these two sets of graphs. We can probably start off by talking about the drain scenario first. So we have to understand this to be able to navigate the concept of consolidation. So let's look at total stress first at the top. So we have some hypothetical soil layer that we load, okay? The total stress can be a surcharge, it can be a blanket of soil that we put on top, can be anything, a total stress that we put on the soil. What happens initially? Well, we have sigma naught. So this is the initial stress somewhere in the ground, it doesn't matter where. And then let's say we have on the y-axis we have stress, and on the x-axis, we have time, y-axis we have stress. And we can see that with time that this load is ramping up. What does ramping up mean? Well, maybe we're putting a sand blanket on and we can only put the sand at a certain thickness and it takes time to reach the total thickness. And afterwards, we plateau in total stress. What does that mean? We're not applying any more change in total stress to the soil. And we can see that relative to sigma naught, this is the change in total stress that we've applied to some element of soil on the ground. Now, for a drain condition, remember the chip bag, we're allowed volume change, right? Because we don't generate any excess pore pressure because the rate of loading is so slow that everything can dissipate. Now, what happens volumetrically? Well, at initial stress, sigma naught, we have an equivalent V subscript naught, and as we increase and ramp up the stress applied, our soil compresses. And when the soil compresses, soil grades, rearrange, and we get compression, volume reduction in the bulk. soil void mixture. Now, once we stop applying the total stress and we reach a plateau, for a drain condition, we're not going to get any more volumetric change. We're not talking about creep at this point, okay? We're just talking about primary consolidation. Likewise, what's happening with the pore pressure? Well, we talked about that already. Well, for pore pressure, for a drain condition, we apply the load so slowly that we don't generate any excess pore pressures. We apply the loading in such a slow way that the pore pressure will just dissipate without generating excess. An excess of hydrostatic, that is. That's what we mean by excess pore pressure. So for drain case, we have U naught initially, and even as we apply loading, we're not getting any increase in pore pressure because it's drained. Everything is transferred nicely to your soil skeleton without causing any abrupt change in pore pressure. What we care about the most as geotechnical engineers is perhaps effective stress, because that governs the fundamental response of soils. It's always effective stress, effective stress, effective stress. What's happening with the effective stress? Well, since the pore pressure is not changing, what does that mean? Well, we know that total stress is effective stress plus pore pressure. Well, if you're not getting any change in pore pressure, any total stress you apply to the soil is going to be transferred to the soil skeleton. And well, that's good for us. That means stronger soil. And we can see that initially, if your effective stress is sigma prime naught, you'll ramp up in the same manner as the total stress. So the total stress would be equal to your effective stress. And that's exactly what we see here in the effective stress plot. It's more or less the same pattern as this. And you have no change in your pore pressure. So that's an idealized drain condition. Okay? So this is just to refresh your memories in case you forgot fundamentals of soil mechanics from your earlier classes. So I guess drain case is easy enough to understand. How about undrained case? Well, let's take a look at the undrained case. Now let me remove some of this. And we focus on the undrained case over here. Now for the undrained case, we look at the same graphs. Okay, total stress, volume, pore pressure, and effective stress. We just shift laterally towards the right of the slide. So for total stress, what happens for an undrained scenario? Well, we tend to like to say that undrained loading occurs rapidly. We talked about that already. Rapid undrained loading. There's no time for pore pressure to dissipate. Fine. So initially, we have sigma prime, and we apply a stress to a soil. And notice that the time frame here is very short compared to this one here. So it's rapid undrained loading to the soil. And we quickly reach our target stress, delta sigma, and it plateaus, meaning we no longer further apply any total stress. So what happens to volume or pressure effective stress for undrained loading? Well, we apply loading, but volumetrically, if we look at this window here, let's just look at this window for now. Okay, ignore the window afterwards. So we have initial V naught, and during undrained loading, well, you get no change in volume because no pore pressures can dissipate from your soil. And this is what we expected. When we apply loading to the chip bag, the total stress is transferred to both the fluid and the chips, but there's no expulsion for fluid. So no volume change, right? And what happens to the pore pressure response? Well, the pore pressure response shoots up rapidly, even though you can't dissipate it from U naught. And there's no immediate change in effective stress because we can't dissipate any pore pressure. So the effective stress remains unchanged. You still have initial sigma prime naught. You haven't had any strength increase. Strength increase comes from consolidation. Strength increase comes from dissipation of pore pressure. So good. So that's the process there. But For an undrained scenario for a reclamation project, yes, this is a very idealized, within this time frame, that's a very idealized undrained loading process. But subsequently, for any reclamation project, yes, the clay may initially behave undrained, but with time, let's talk about months, weeks, years, you do get volume change because the point of generating this total stress and increasing the pore fluid pressure, increasing the pore fluid pressure from here is to dissipate it, right? When we dissipate the pore pressure, then we can get an increase in effective stress. So what happens volumetrically? Well, volumetrically, after some time, when your pore pressures can dissipate in your soil, nothing is impervious, right? You see that you have dissipation of pore pressure with time, and as you dissipate the pore pressure, the volume proportionally decreases. Likewise, what happens? Well, conversely, your effective stress will increase. So we can see the differences between a drained, perfectly undrained, and an undrained scenario transitioning to a drained scenario, right? So that's what these graphs show us. So that's exactly what we're trying to do when we carry out land reclamation to improve a slab of clay, for example, marine deposits, so we can build on top of it. These are the principles we're trying to adhere to. And also, some of these concepts can be applied to triaxial testing as well. It's the same concepts. This is also a very popular model when we deal with consolidation that we see. So this is the spring piston analogy. This spring piston analogy is, I guess, analogy to saturated clay. I just want to bring this up because it's quite easy to understand what's happening as well. Let's say you didn't understand the graphs before. Well, let's take a look at the spring piston analogy. Let's take a look at one schematic at a time. So we often use the spring piston analogy to understand the concept of consolidation. If you look at the spring represents what? It represents the soil skeleton. In this case, we have closed valve, you have saturated clay. Closed valve means you're not going to dissipate any pore pressure. We haven't applied any load on here yet, so there's no change in excess pore pressure. So that's the initial state of our soil. Now, if we move just to the right-hand side, we apply some load, P, to this spring. The valve is still closed. So what's happening? Well, the valve is closed, but we've transferred this load to our soil, and we see a proportional increase in change in pore pressure due to this load. You can imagine that some of this load was transmitted to the pore fluid. Now, what happens when we open the valve? When we open the valve, we get dissipation of pore pressure, and we can see that, well, we get compression in the soil. And the change in pore pressure is less than that initially applied in step B. And why is that? Well, the load is gradually being transferred to the soil skeleton. And later on, if we keep on letting the valve remain open, and you'll dissipate all your pore pressures, and your soil compression will be very profound. And this is what we refer to as the end of consolidation, when your excess pressures are dissipated. Now, this block P here is basically what we would do in the field for reclamation when we dump a sand blanket or a fill layer for surcharging a soil. We essentially want to generate excess pore pressures, dissipate them so that this clay or MD layer will compress. And when it's reached a stage where it's finished primary consolidation, we're not worried about unwanted settlement later, and then we can start construction on it. Another added benefit of consolidation is, of course, you get increase in strength in the soil. So this is just another analogy to describe the process of consolidation. to really see what's happening in terms of pore pressure. For any reclamation project in Hong Kong, we often see some sort of soil geology like this. So this is MD, okay, marine deposit. ALL is alluvium, and maybe this is rock. Okay. So this is rock. So normally our main concern is this layer, because if we try to build on it, it'll compress. So there are a few ways to treat this, but the primary objective of all these ways is still the same. We have to consolidate this layer, so we compress it, and it doesn't cause us problems later. You can fill this with, let's say, dump sand on here. You can dump sand all the way here. It can be some fill material, but if you dump sand on here, what happens? Well, this empty layer will compress. The fill layer can be what you assume as the surcharge or total stress applied to it. And when the empty layer compresses, yeah, well, your fill layer will also settle, right? Because the same amount that your empty layer compresses. At the same time, your fill layer can also compress as well, okay? But based on this analogy, try to picture this now. This can be our empty layer, and we apply some fill layer on top. Interestingly, we have double drainage here. So what happens in terms of variation of stresses in an MD or clay layer with double drainage? Well, let's look at this problem by applying all the conceptual principles we talked about already. So in this case, we have sand, clay, sand sandwich. And we apply some sort of change in total stress on top of this sandwich here, this clay sandwich. The groundwater table is located at this point, so this would what we would use to decipher or describe the hydrostatic conditions. And because there's sand on top and below the clay layer with initial thickness H, excess pore pressures can dissipate in both directions, and we call this double drainage, as you remember from your soil mechanics class. Now, when we apply this total stress to the soil, initially, we have a perfectly undrained condition. So we have an increase in delta sigma. All the load is transferred to your pore pressure increase. But since none of the, not all the load is transferred to your pore pressure, but there's no change in pore pressure. So there's no change in effective stress because you haven't dissipated your pore pressures to increase the effective stress. So there's no increase in effective stress. Now, after some time, what happens? So we call it between initial loading and when primary consolidation finishes, infinity. Is, well, pore pressures will start to dissipate near the top and bottom of this clay or MD layer. And you'll see that pore pressures become, excess pore pressures tend towards zero, and they're the highest near the middle of your clay layer. And you can see that with time, these pore pressures will dissipate, and this blue region will get smaller and smaller. And we know from the concept of effective stress that effective stress is proportional to the dissipation of pore pressure. That's why we see that there's an increase in effective stress now proportional to this shape, which would fit directly here. And where most of the pore pressures have dissipated near the boundary, that's also where you get the largest increase in effective stress. Now, if you look at this and you think about some of the theory that we'll go over after, within a certain layer, the rate of pore pressure change is not uniform, right? So this is a problem with some of the assumptions we make in our theory, but just food for thought. Near the end of a consolidation process, what happens? Well, all the total stress should have been transferred to effective stress because you have dissipated all your pore pressure. So all the total stress applied would have benefited the effective stress. So this is what's happening for a clay layer. Now, if we look at, let's say, these piezometers, so each one of these is a piezometer. The piezometer enables us to look at the change in head or pore pressure locally at a particular point. So we have 1, 2, 3, 4, we have 5 points, right? Now, this time frame here, initially, we can see that at time equals 0, just after we apply the load, we have a uniform increase in pore pressure, just like we do here, right, with depth. So it's uniform. When time is between or after undrained loading, we see that there's a change in the head. And these two here are near the boundaries. That's why the pore pressure is the lowest. And after primary consolidation has occurred, what happens? Well, the level of the piezometers are the same as hydrostatic level. So everything has reached the initial state, hydrostatic state. So nothing is in excess of hydrostatic. That's why we call it excess or fluid pressure, anything in excess of hydrostatic. So this is the gradual process of what happens during fill surcharge onto a slab of clay. And these are the very basic principles that we use from our basic soil mechanics class. And in essence, this graph here explains the concept of consolidation, which is ultimately to transfer the total stress to the effective stress. But it takes time, especially for clay. So that's the recap I wanted to go over. So these are the concepts you should have learned from your soil mechanics class. I guess you were taught by Jin Hung Chu, probably, right? Soil mechanics? Am I right? No? Or who taught you soil mechanics? Jin Hung, right? Yeah, okay. So I hope that was a recap, stuff you should know, like the back of your head. Now let's jump back to the topic at hand. So before we do that, we talked about the differences between compaction and consolidation. Now, compaction, we apply some sort of mechanical energy just to remove some of the air from the soil, partially saturated soil, to increase the dry density. We don't really change the moisture content of the soil much. Now, in contrast, for consolidation, we apply some total stress or external load to the soil, and with the premise of dissipating any excess pore pressures we apply or generate. So after consolidation, we should see a significant reduction in void ratio and a change in the moisture content. So these are the fundamental differences between the two methods of ground improvement. Just for your interest. Now, now that we finished the first outcome that I wanted to achieve, the second outcome is, well, let's try to remember your favorite topic, odometer testing. Everyone, or each one of you have done this in the lab and should remember the concepts. So odometer testing is what we use when we get samples from the field, undisturbed samples, relatively intact. We bring it to the lab to try to get consolidation parameters so that we as geotechnical engineers can calculate and tell the client how much compression we need, how much sand we need, how long will this take, right? So the odometer will reveal a lot of important parameters for us. In case you forgot how odometer looks like, well, that's how it looks like here in the top right. You have your soil specimen here. You have a pervious disc sandwiching the soil specimen, and you have some sort of loading yoke here. And you have a dial gauge to measure the compression of your soil, and for more old school devices, you can apply the weights manually to the lever arm, and then the lever arm applies the load to the loading yoke. And if you want the blown up view of what's happening with the soil specimen, you have porous disc, soil, porous disc, and it's more or less a 1D type situation, right? That's what we're assuming, one-dimensional. So that's what odometer looks like. And The real things we're trying to measure, well, how much load do we apply? Well, we know that because we have put the weights on there ourselves. And how much compression we're getting on the down gauge. These are the things we're trying to measure. Ultimately, with any odometer test, we can get a time deformation plot. We can record the time each time we take a measurement. And there are a few stages on a typical time deformation plot. We have, in the first stage, we have some sort of initial compression. In the second stage, we have primary consolidation. So this is our primary compression. And if you remember from your solid mechanics, some inflection point here will give you the pre-consolidation pressure. We can talk about that in a bit. This curve here is our primary consolidation. And for typical soils, we'll have some sort of inflection again. And the region here is our creep, our secondary consolidation. So we all remember this from our solid mechanics class. And this is a very telltale curve. So any initial compression is mostly created by preloading. Primary consolidation, deformation is caused by dissipation of pore pressure and transfer of total stress to effective stress. And as we mentioned, secondary consolidation takes place once all excess pore pressures have been dissipated, and it's mostly readjustment of the soil fabric. So you have deformation without any change in total stress and effective stress, right? So if we want to do any calculations regarding consolidation, we have to again look at weight, volume, mass relationships. We have a height of the initial specimen here, so we can see that the black dots and the white texture here characterizes soil. You can imagine that black dots represent soil granules, and the white part represents the voids. And we have initial height, uppercase H, and if we break down this black and white texture into just voids in soil, then you can get purely voids, this region here, and pure solids from the grains, which is shown as the black. And you can further break this down into characterizing change in volume by change of height. Now, let's say we have increments where we have change in height 1, you get this drop here, change in height, you get this drop here. So this is what we would characterize during odometer testing. Now, if we want to formulate very simple expressions on the height of the voids, we just take the total height of the initial specimen minus the height of the solids, which is here, right? And if we want to calculate the height of the solids, we know from the weight-volume relationships that that's just the weight of the solids divided by specific gravity times the unit weight of water. So let's work out some basic relationships for odometer testing. So I just showed you the curve. Now the question is, how do we use this curve, right? To calculate variables that we want to know for reclamation projects. Well, the first thing you would do is you would calculate the height of the solids, and we already talked about how this relationship is something you should know from basic solid mechanics class. You can convert the weight back to mass if you'd like. So that's how you get HS, and once you know HS, you can calculate HV automatically. So as we mentioned, if you know HS from this relationship, then you can calculate HV here. After you calculate HV, then you can calculate the initial void ratio. And you know the void ratio is the volume of voids over the volume of solids. And in our case here, we can break up volume of voids into the height of voids times the cross-sectional area of our specimen. And if we cancel this out, then we know that the initial void ratio is related to the height of the voids over the height of the solids. So where are we trying to go with this? So if we carry out steps 1, 2, and 3, we can start to deduce any change of void ratio per incremental load that we apply to our soil specimen. So let's take a look at the first incremental loading. We refer to it as subscript 1, or 0, 1 in this case. And subscript 1 will cause an incremental deformation of delta H1. So this is what we're doing in the odometer test, right? Each time we get dial gauge reading, we get the change in height. That's what change in height in 1 is. And we get change of height, subscript 1, after we apply some loading to the loading yoke for the odometer. If we want to calculate the change in void ratio relative to the height of the solids caused by the increment, then we know that we can calculate change of void ratio by delta H subscript 1 over the height of solids. And how do we get H delta H01? Well, we just read it off the dial gauge from the odometer testing. So when do you know that you can take a reading? Well, you can take a reading, and it's important to know that total stress should equal to effective stress at that point, because this should be drain loading, right? We shouldn't generate any excess pore pressures during this process because we consider it a drained loading scenario. That's why we can leverage these relationships. So we do the same thing for each step. If you have a second loading increment, you get a second compression of H2. And if you know the void ratio change from your initial void ratio, then you can plot this entire void ratio versus effective stress plot out. So we have void ratio on the y-axis, and we know our effective stress y because we know that any total loading for drain condition should be equal to the effective stress, right? Because we're not supposed to generate pore pressures. So how do we know this? Well, we just wait for a very long time for the soil to equalize before we apply the next stage of loading to the odometer test. And you just keep on repeating this process. And you can get you know your initial void ratio, you know the change in void ratio, E1, and you keep on applying loads, E2, E3, E4. And for the next loading, we can call it sigma subscript 2, and you get additional deformation of delta H02. And similarly, you can calculate the incremental change in void ratio, and you can map out this void ratio versus effective stress plot. And like I said, similarly for the first weight, the total stress must be equal to the effective stress for drain condition. And you keep on doing this until you can map out a curve that you like. And this void ratio pressure plot is what we can use to calculate change in thickness of a particular soil. We can cover this in the next class. I think we're out of time now. So yeah, we'll carry on the next class. Thank you for your time.